Hello, everybody. Welcome to today's lecture. So today we're going to start talking about 2.5. Last time we talked about 2.4, which was multiples and factors. So we talked about what it means to be a multiple of a number, which was kind of like counting by that number, right? Like if you wanted to find the multiples of fives, you would just count by five. So 5, 10, 15, 20, etc. And then we talked about divisibility. How to tell whether or not a number is divisible by certain numbers like 2, 3, 5, 6, and 10. I think that was all of them. You can see right here, yeah, 2, 3, 5, 6, and 10. And then we talked about how to find the factors of a number, and what it means to be a factor of a number. And we went through how to find some of them just using divisibility. We're going to really expand on this today, though, because we're going to talk about the prime factorization of a number. Okay. So before we do that, before we talk about prime factorization, we need to know what prime means. Okay. So let's start with that today. So a definition, a prime number is a number that is only divisible by 1 and itself. Okay. A prime number is a number that is only divisible by 1 and itself. Okay. So what would be some examples of these numbers? Well, let's think about it. An easy first example is 2, right? 2 is divisible by 2 and it's divisible by 1, but there's not any other numbers for it to possibly be divisible by. Because if a number is to be divisible by a number, the other number has to be smaller. There's no whole numbers or counting numbers smaller than 2 other than 1, right? So it's divisible by 2 and 1. So kind of by default, it's a prime number. It's also going to be the only even prime number because any other even number is automatically divisible by 2. That's really what it means to be even. So let's look at the next number, 3. 3 is not divisible by 2. It's only divisible by 1 and 3. Okay. So so 3 is prime. I think I should mention every number is divisible by 1 and itself. Okay, every single number will be divisible by 1 and itself, every counting number. So from 1 onwards. 0 is not, for example, divisible by itself. So the special part here is that it's only divisible by those numbers. So we don't need to check whether or not it's divisible by 1 in itself. It always will be. We just need to know, are there any other divisors? Okay, and it can be very hard to check. So we're not going to be typically checking for that. Instead, we want to just be familiar with some of the smaller ones. Okay, so the next one's going to be 5. So possibilities, it could be divisible by 2, 3, or 4, but it's not. 7, we'd have to check if it's divisible by 2, 3, 4, 5, or 6, right? And it's not. So it can only be divisible by the number smaller than it. So you can see we can already eliminate all the even numbers because those are all going to be divisible by 2. So we're only looking at odd numbers now. What about 9? Well, 9 is divisible by 3, so 9 is not prime. So now we go to 11. 11 is prime. And then 13. 15 is not prime. 15 is divisible by 5 and 3. 17 is prime. 19 is prime. 21 is not because it's divisible by 7 and 3. 23 is prime. 29 is the next prime, then 31. And this can go on forever. Okay. 37, 41. These are prime numbers. And I'll just write etc. at this point. Okay. So these are all prime numbers. And this would go on forever. There are an infinite number of primes. which can be surprising because you might think that they would run out, because as numbers get bigger, there's more and more numbers that it could be divisible by, right? Once you get to a million, there's, or let's say 1,000,001, now there's like a million numbers that it could be divisible by, right? But it has been proven by the ancient Greeks, actually, so it's been known for a very long time, that there are an infinite number of prime numbers. Okay. So why do we care about this? Well, prime numbers are very special numbers. The fact that they're not divisible by anything else other than one in itself it's very unique. And in this way, like we're going to see with prime factorization, it's kind of like the atoms of numbers. Atoms from chemistry, right? Atoms are what makes up everything. So you can break anything down into its atoms. Like this microphone, right? You can take it down, whatever kind of metal it has. Um, I'm sure there's paint on it, right? Whatever kind of elements the paint is made out of. Like you can break them down into its elements, into the atoms. Same way here, with any number, we can break it down into its prime numbers. That's what the idea of prime factorization is. So it's like the building blocks of numbers, which in turn, and the numbers are the building blocks of math. So prime numbers are, transitively the building blocks of math. So there are entire areas of math and mathematicians' entire careers dedicated just to solving prime numbers. Not solving prime numbers, sorry, studying prime numbers even today. There's a area of math called number theory, and one of the key parts of number theory is just studying prime numbers. Okay. I don't know a lot about the area myself, but if you think about cryptography, right, cryptography like code breaking, it's very useful in computer science, like protecting things like passwords, bank accounts, that kind of stuff. In cryptography, prime numbers are very important because if you're kind of like brute forcing the numbers, if you're using prime numbers, then it's very hard to detect them because they're not divisible by anything. Okay, I can't explain it super well because I'm not familiar with that math. That's just kind of like what I've heard about cryptography, but that's just one of the ways that prime numbers are applied in our lives today. And there's still a lot that's not known about them. For example, like if there's a pattern to them, which would be very useful for, like I said, cryptography. Okay. So what do we call numbers that aren't prime, right? Obviously, as you can see, there's a lot of numbers here that aren't prime. Well, a number that's not prime is called a composite number. A number, whoops. A number that is not prime is called composite. Okay. Composite. So we have all numbers, all whole numbers are either composite or prime. So what we want to do today is talk about the prime factorization of a number. So remember, factors of a number are when you break a number down into two numbers that when multiplied together give you that original number. So like 72, you break it down into 9 and 8. So essentially you're breaking it down into smaller numbers. With prime factorization, what you do is you keep going until all that you have left is prime numbers, and then prime numbers can't be broken down anymore, right? Because they're only divisible by one in itself. So you can take any number and break it down into only prime numbers. And that's what I meant by they're like the building blocks of all numbers. So let me see how to word this here. The prime factorization of a number is the number written as a product of prime numbers. Okay. So we take a number and we write it as a product of prime numbers. And one of the special things about numbers is that every single number can be written as a unique product of primes. So every number has its own prime factorization. So let's look at an example. Okay, let's take an easy one like 9, right? 9 is equal to 3 times 3, right? And 3 times 3 is a product of primes, right? 3 and 3. So this is the prime factorization of 9. Okay. One thing we should note is we typically only talk about this with composite numbers, because if a number is prime, then it already can't be broken down anymore, right? So like 41, for example, 41 is prime, so we can't break it down anymore. So this is the prime factorization of 41. It's just itself. Okay. Let's think about 72. We used this for factors last time when we found that it's equal to 9 times 8. But we can keep going further, right? 9 is equal to 3 times 3, and 8 is equal to 2 times 4. And now we're still not quite there because 4 is not a prime number. The rest of them are. So now we can just keep going. We break 4 down into 2 times 2, and now we have 3 times 3 times 2 times 2 times 2. Okay. So that's the prime factorization of 72. Oftentimes we'll write it with exponents, so you don't have to write the number over and over again. And we'll also write them in order, so we'll write the 2's first, then the 3's. So there's 3 copies of 2, so we write 2 to the third power. And there's 2 copies of 3, so we write 3 to the second power. Okay, so either this or this, either this or this would be acceptable. So these are the prime factorizations of 72. A good way to organize this is using what's called a factor tree. Okay. So let's learn this by example. Let's take like the number 105. Okay. So we start with the number 105. You might want to check real quick to make sure it's not prime. 105 isn't because it's divisible by 5. And then we kind of make branches off of it here, like a tree, into 2 different factors. Okay. So it could be any 2 factors. Here we know 5 is a factor, and it's going to be 5 times 21. Okay. So 5 times 21 gives us 105. So we broke 105 down into 5 times 21. Now 5 is prime, so we don't need to break that down anymore. So we can go ahead and circle it so that we know we're done with it. Now the number that's not circled, 21, we need to keep breaking that one down further. And we can break that down into 3 times 7. Okay. 3 is prime, 7 is prime, and now we're done. Okay. So now we take all of the circled numbers, and this is the prime factorization of 105. 3 times 5 times 7. Yeah. All right. Let's just keep doing some more of these here. What about 36? Okay. Well, 36 is like I said, there's a few different ways you could do it. Maybe you do 3 times 12. Maybe you do 6 times 6. Let's do both of those. Okay. We'll do the other one here. I'll write it over here. Maybe you think of 3 times 12 first, right? Let's focus on 6 times 6 first, though. So neither 6 nor 6 are prime, so we have to break those down further. So we can break 6 down into 3 times 2, and this 6 down into 3 times 2. And now all of these numbers are prime, so now we're done. Okay. So 36 is equal to 2 times 2 times 3 times 3, aka 2 squared times 3 squared. Okay, so you can write it with exponents or without exponents. Either one of these. So now going over to this one, we broke it down into 3 times 12. Well, 3 is prime, so we're done there. But now 12, that can be broken down further. So then you just do whatever comes first to your mind. Like the first thing that comes to my mind with 12 is 3 and 4. So 3 is prime and 4 is not. So we got to break that down further. We can only break that down into 2 and 2. So there we go. All right. And we get the same thing that we got over there. Okay, 2 times 2 times 3 times 3. So it doesn't actually matter what your branches look like. These trees look completely different, but we end up with the same answer. Okay, as long as you're going until the number is broken down into prime numbers. So this is why I said, like, we don't normally need to check if the numbers are prime. We just need to be familiar with the lower prime numbers. Like, if you memorize this whole list that I have up to here, that would be more than enough, right? You probably don't even need to go that far with it. Typically, we can break things down into just the first few. Okay. Let's do a few more here. Here's a good one from the book, 294. Okay. It's a little bit trickier. I like to just start with, if I don't know a bigger factor than it for it, I know that's divisible by 2 because it's even, right? So we can start with that. And, we can just do the division by 2 over here on the side. Or you can just use a calculator, but I'll just show it on the side here. Okay, so we get 197. So 197 is a little tricky. I don't know what that's divisible by. Let's think about it. It's not divisible by 2. It's not divisible by 3 because 1 plus 9 plus 7 is 17, right? Which is not divisible by 3. Not 5. We can try 7. This might be a tricky one from the book. Maybe this was a bad example. We'll see. We'll just roll with it. This is not going to be divisible by 7. I can already see the long division's not going according to plan here. Or maybe it is. Did I do the long division over here wrong? It says it should be divisible by 7. Let me try this again. So we have minus 14 is 5. What am I? Sorry, I'm doing something wrong here. Do we do this long division wrong? Let me see. So we do 294 divided by 2. Oh, it's 147. Why am I getting 197? What did I do wrong here? Sorry, let's start this over. Okay. And this is no problem. This is a learning experience. This is how math gets done. We roll with it. I can already see what I did wrong. I did -2 equals 1 here, I think, because I had a 19 here. So that's what the issue was. So 2 goes into 9 4 times. There we go. And now we get 147. There we go. All right, I apologize for that. So 147 is still pretty tricky. We can already see it's not divisible by 2 or 3 because we can do, this is equal to 12. Oh, it is. All right, it's divisible by 3 then. So that actually makes it a bit easier. Yeah. So we add the digits up and we get 12. 12 is divisible by 3, which means 147 is divisible by 3. So now we have to do some long division correctly, hopefully this time. And this is 4 minus 12 is 2, 7. 3 goes into 7, 9 times, 27, 9 times. Okay. So we get 49. So there we go. By the way, we were done with 2, so we could circle it. Done with 3, so we can circle that. What about 49? Well, if you know your multiplication tables, 49 is 7 times 7. Okay. So there we go. So we're all done here. So 294 is 2 times 3 times 7 times 7, or if you prefer, 2 times 3 times 7 squared. Okay. Even if you don't want to use the exponent notation, you should get used to it because that's what the book uses most of the time. It actually presents most of the answers as both, but I think eventually it ditches the former for the exponent notation. Okay. So it also talks about the ladder method. I'm not going to go through the ladder method because, I mean, there's really no reason to use another method. This method works perfectly. In my opinion, I've never seen anybody prefer the ladder method. So if you want to go through it, it is in the book. So feel free to go through it. If you use it, it's fine. I'm never going to ask you to use a particular method. I won't say never, but in general, I'm not going to ask you to use a particular method. I'm just, I just want you to use a method and get the right answer, right? I'm going to give you all the tools and the methods that you need. You decide which ones to use, okay? Now, if you use a method incorrectly but still get the right answer, that's a different story, right? I'm not grading you on the answer. I am grading you on doing the proper method. So the method is important. It's just that which method is not important, okay? Let's go ahead and go to the next part of this chapter, the least common multiple of two numbers. So this is going to be very important for when we start talking about fractions, which is going to be very soon because chapter 3 is super short. So chapter 4 is where we start fractions. So it's going to be very soon. We, in fact, we might even do chapter 3 today because it is so short. So the least common multiple is going to be very important to us. The least common multiple is exactly what it sounds like, okay? Hang on one second. Excuse me, just had to sneeze. The least common multiple of two or more numbers is the smallest multiple that they have in common. Okay. So we abbreviate it with LCM. Okay. So the LCM, the least common multiple of 2 and 3 is, well, what is it? Well, let's look at the multiples of 2, right? The multiples of 2 are 2, 4, 6, 8, 10, etc. Okay, so this is what we did last time. The multiples of 3 are 3, 6, 9, 12, etc. So the smallest one that they have in common is the 6. Okay. So, the way we might write this, you can just write it out in words. Like you can just write it up here is 6. Okay. Sometimes you might see it written like this. Least common multiple of the two numbers in the brackets is 6. Okay. So I'm trying to think of how to word this. Sorry. One thing that's very similar to the least common multiples, which I don't think is ever talked about in the book. I'm trying to think if I skipped it last time. But it's called the greatest common factor. Okay. The greatest common factor would be you break the numbers down into factors and look at the biggest number that is a factor of both of them. I.e., what's the biggest number that divides both of them? And it can be useful for a least common multiple because what you can find is that if the greatest common factor of two numbers is 1, then the least common multiple of the two numbers is just the two numbers multiplied together. Okay. Let me see if I did skip it. I don't think I did. Yeah, I think it's just not in this book. So that's okay. We'll proceed without it. It's not necessary. So there's a couple of different ways to find the least common multiple. One is like we just did. We just list the multiples and then we find the ones they have in common. The other is using the prime factorization. Okay. So let's do this method for a few more. Let's look for the least common multiple of 10 and 15. Okay. Well, for 10, we have 10, 20, 30, 40, etc. 15, we have 15, 30, 45, 60, etc. So 30, that's the smallest number they have in common. Okay. So we just list a few of them, and then look to see if they have one in common. If there's more than one, we take the smallest one. If they don't have anything in common, then you would just keep listing until they do. Okay. Let's think about 9 and 8. Okay. So for 9, we have 9, 18, 27, 36, 45. For 8, we have 8, 16, 24, 32, 40. So we look at these lists, there's still nothing in common. So we just need to keep going until there is something in common. So for 8, we have 48, 56, 64, 72. For 9, we have 54, 63, 72. Okay, so 72 is the first number they have in common. Okay, so there we go. The least common multiple of these is 72. So, I mean, as you can see, like, it can get kind of tedious, right? You have to, if you you have to list all of these multiples, which can be time consuming, and you have to wait. You have to keep doing it until one of them having them in common. Even this is relatively soon, right? It's on like the 10th factor or so. What if it's not to like the 100th factor? So that's where this next method comes into play. Okay, prime factorization method. And I should also mention, like, as you get practice with these, it might just kind of come naturally where you can just look at the numbers and be like, oh, the soonest place they're going to meet is this number. And that's fine. You don't necessarily have to do either method. Like, after a while, you'll be able to recognize like the least common multiple of 2 and 6. Oh, that's 2 and 6. Oh, that's 6, right? The least common multiple of 2 and 3. Oh, that's 6. Like, with the small numbers, that's fine. But there will often be large numbers where that would be impossible. Okay. So for the prime factorization method, we take the prime factorizations of both numbers. Okay, so let's take like 10 and 15, for example. Okay. So first we write the prime factorizations of the numbers. So these are relatively small numbers, and they only really have one choice, right? So for their least common multiple, what we do is we look at what they have in common. Okay. And sorry, let me think about this for 1 second. Okay, yeah, I was doing the multiplication wrong in my head, so I thought we were going to get the wrong answer, but we're not. The way we find the least common multiple, once we write out the prime factorization, we look at the numbers they have here. Any number that they don't have in common, we carry over. And any number that they do have in common, we only carry over one time. Okay. So there's a 2 here, so we brought it over. There's a 3, which we brought over. And then 5, they have that in common, so we only need to bring it over once, even though both of them have it. Okay. And then this product will give us our least common multiple, which is 30. So with the numbers like 2 and 3, it becomes simple because they're their own prime factorizations, right? Because they're prime numbers, so you just do 2 times 3, so you get 6. What about 9 and 8? Well, 9 is 3 times 3. 8 is 2 times 2 times 2. They don't have anything in common. So you just bring them all over, which is essentially just 9 times 8, right? So you get 72. So you bring over the factors, but if they have them in common, you only bring them over once. What about 15 and 105? Okay. Maybe that's not a good one. How about 20 and 105? Okay. So this is one, it would be very hard to do in our head. It'd be very hard to do with the multiples method. Because 105 is a big number, right? And they're also very far apart, so you'd probably have to list a lot of multiples of 20 before you even get close to 105. So this is definitely one we'd want to try this method on. 105, we already found the prime factorization of. It was 3 times 5 times 7. 20, we need the prime factorization of. Let's do that down here. Okay. So we break it up into whichever two numbers you prefer, maybe 4 times 5, right? 5 is prime. And you break 4 up into 2 times 2. So 20 is 2 times 2 times 5. So they have this 5 in common. Okay. So their least common multiple, we're going to have 2 times 2 times 3 times 5 only one time because they have it in common, times 7. Okay. And then we just do that multiplication. Let me just do it in the calculator here. 2 times 2 times 3 times 5 times 7 is 420. Okay. So we write the prime factorization of each. If they have something in common, we only use that number once. Okay. So what happens when we have something like 2 and 12? Well, in this case, one of the numbers is divisible by the other number. Okay. So automatically, the least common multiple has to be the bigger number. Why? Well, if we look at the list method, right, with 12, the first multiple is always going to be itself. So that's the smallest possible multiple of 12. And 2 is going to hit 12 because, like I said, 12 is divisible by 2. You can write it out just to confirm. Right. So there we go. If we wanted to do the prime factorization method, 2 is just 2. 12 is 2 times 2 times 3, like we did earlier, right? So they have a 2 in common. So the least common multiple is going to be 2 times 2 times 3, which is 12. Okay. So if one number is divisible by the other number, the least common multiple just has to be the bigger number. Okay. If it's two numbers that don't share any factors, like 3 and 2 or 9 and 8, or any two prime numbers, they don't have to be prime though. It's just going to end up being the product of those numbers because they have to share a factor in order for you to only count that factor one time. If they don't share anything, you're not only counting anything once, so you're just going to end up multiplying the two numbers together. Okay. Okay, so I think that's good for this section. Definitely practice some of these because like I said, this will come up when we look at fractions. We're gonna have to find the least common denominators. We can usually get away with just finding a multiple instead of a least common multiple, but it's useful to find the least common multiple. And it'll of course be on the homework as well. Okay. So I think we'll end it there today. I think we'll just have a short one today, and then I'll put all of chapter 3 into one video. Okay. So thank you for watching this video, and I will see you guys on the next one.